A Portland Community College Mathematics Telecourse. A course in Arithmetic Review, produced at Portland Community College. Let's recall the problems we looked at very briefly 2 lessons ago. First problem, a tree of unknown height cast a shadow 26 feet long at the same time and place that a 36-inch yardstick cast a 13-inch shadow. Or this one, a trucker covered 465 miles in 4.2 hours. At the same rate, how long will it take to drive 706 miles? Notice that those problems had the following in common. Each deals in a repeated situation. The last problem, a certain distance in a certain time. The repeated situation, a different time and a different distance. But the 2 situations dealt in distance and time. The problem before that, first situation, a tree and its shadow. The second situation, the height of a yardstick and its shadow. A repeated situation. And each situation involves 2 items which are so related that if one were to double, then the other would also have to double. It's simply the nature of their relationships. Let's check that out. The tree problem. It stands to reason that if on the same ground at the same time, that if the tree were twice as high, its shadow would have to be twice as long. The trucker situation. If he's driving at the same rate, which it says he is right here, then if he were to drive twice as far, it would take him twice as long. Again, each situation involves 2 items which are so related by nature that if one were to double, the other one would also have to double. Such a situation will be called a proportionate situation. Now let's translate those problems to mathematics. The first thing you'll do is to identify the 2 proportionate items. In the trucker problem, the 2 items were distance and time in hours. Let's note that on a scratch paper. We're dealing in distance in miles and time in hours. Now please note this. The order that you write those 2 items is unimportant. You can write this one first, this one second. You can write one up, one down. The order is totally unimportant, providing you keep with that order within the problem. Next, we're going to write down one of the 2 situations as it relates to those 2 items. In the first situation involving the trucker, and we'll call that here situation 1, his distance was 465 miles and his time was 4.2 hours. Next, we will write down the second situation in that same order. Now, in the second situation, we want to know the distance. Well, that's 706 miles. So since miles is written first here, it will be written first here. Then we wish to know the time, but that's what we don't know. It says how long. So let's use T for time, or H for hours, or X for an unknown, or an N for number. But the important thing is this. We have a situation, 465 miles in 4.2 hours. This order was unimportant as long as the next situation has the same order. So distance, distance, time which is known, time which is unknown. Now, after you have written it down in that way, to establish the proportion which we're going to solve, which will resolve the problem, is this simple. Just that simple. And to solve the proportion, we take top times bottom, 465 miles times the unknown t, set equal to, and don't forget this, the bottom times the top. The two cross products are set equal to each other. So 706 miles times 4.2 times hours. Now note, we kept the units right with it. That's an important part of the problem. Remember, we stated this is not the number 465, it is a number 465 miles, a measurement number. This is not the number 4.2, it's the measurement number 4.2 hours. So keep the measurement units with the problem. You'll find it will give us a way to check. Quickly, top times bottom, set equal to bottom times top. Now divide both sides by the multiplier of the unknown, which is the 465 miles. So I'll divide both sides by 465 miles. And of course over here it'll all cancel off, isolating my unknown. And on this side, notice that the mile cancels with the mile, leaves me with hours as my unit, which tells me my time is going to be in hours, and that is a fact. So that's the way you can check whether you're on the right track. Now the arithmetic here is fairly messy. 706 times 4.2 divided by 465. So it's just as well to use a calculator. So 706 times 4.2 divided by 465 is, and our answer comes out again with an unending decimal, 6.3767 and so on, hours. Don't forget the hours. Now we look back to the problem and see if it specified how we wanted to round it. And it said to the nearest tenth of an hour. So there's my tenth. The digit next to it is 5 or more, so I add 1 to this. So the time is 6.4 hours to drive 706 miles. It might seem complicated, but once you work 2 or 3 problems, repeating the rules to you as you go, you'll find it's a very simple procedure. Let's try that with a tree and its shadow problem. First, we ascertain that we're dealing with 2 items, shadow and height of a tree, such that if one were to double, so would the other. That's what tells us we can use a proportion. Now, the first thing we do is to identify the 2 proportionate items. In this case, it's height and shadow. So let's identify those on scratch paper. Here we have the height of the object and the shadow of the object. And the order of these, again, was unimportant. We're going to have 2 situations. The first situation, recall, was the tree. The second situation, recall, was the stick, which was at the ground at the same time in the same place. If it was a different time, of course, the shadows would get longer or shorter, depending upon the time of the day. Next, we write down one of the situation as it relates to those 2 items. First, the tree. The height of the tree we don't know, so let's call it h. The length of the shadow, they told us that, 26 feet. And again, if it's a measurement, keep the whole measurement, not just the number part. So we've identified the two items with my first situation. One of them was unknown. I used a variable for that. And last, we write down the second situation in that same order. Second situation is the stick, the yardstick. So we want its height is 36 inches. So I'll write that down, 36 inches. And its shadow is 13 inches. So first situation, height, shadow. Second situation, the stick, height, shadow. Now at that point, our translation is over and we have our proportion to be solved. Now some might ask, if this is in feet, shouldn't these be in feet too? The answer is yes. If both of these were in feet, it would work. But let's leave it in inches and see what's going to happen. Okay, we're going to take two cross products and set them equal. So this is h times 13 inches, set equal to 36 inches times 26 feet. Next, divide both sides by the multiplier of the unknown, which is not 13, but 13 inches. Cancels here, leaving my unknown, which is what I'm after. Over here, can we do any cancellation? Well, certainly the 13 goes into 13 once, 13 goes into 26 twice. But note this, inch goes into inch once, and inch goes in inch once up here. So the item we weren't sure about, which was inches, canceled out, leaving us feet, which is what we wanted the height of the tree to be in the first place. So as it turns out, it didn't make any difference if this was in inches or in centimeters or in meters, as long as they were the same here. So by keeping your units of measure in the problem, you can see if all is going well by simply seeing if the things you don't want cancel out and you're left with a thing you do want. If it doesn't come out that way, you know that perhaps you have made an error. So now finishing our problem, we have 36 times 2, which is 72, times feet. So the height of the tree is 72 feet. Now this presents us with a rather tantalizing situation. It's saying if we have a tree, we don't know its height, but it's the kind of a day where we can measure the length of its shadow. And if at the same time we can place a stick into the ground on a ground with the same slope and measure its shadow, that using those things we can measure, we can find the height of the tree indirectly. That is, we're saying the height of the tree is to the shadow of the tree as the height of the stick is to its shadow length of the stick. And that this proportion will allow us to solve for any one of the items we can't solve. Well, it's difficult to measure the height of a tall tree, but its shadow is easy, and a shorter stick is easy to measure both its height and its shadow. So with this knowledge, you can go home and measure the height of any large tree in your yard, or your house itself for that matter, or if you wish, a mountain. If you had a cliff and you didn't know its height, and perhaps there's a river here and you can't cross it, you could sight up here, measure off a certain known distance, sight up here, in this case you can measure this, let's call it x. Now on a piece of paper, draw a triangle with the same shape. But on the triangle you can measure this height, length, which corresponds to this, we'll call it A, and we could find its height, which corresponds to that, which we can call B. But we measured this on site. We've measured these on a piece of paper, so we can say the height of the big triangle is to its base as the height of the little triangle with the same shape as the length of its base, and find by solving the proportion that unknown. So this, proportions, is a basis for all of what we call trigonometry and surveying. And think about how much in our world, in construction, house building, industry, is based on that principle. A simple math idea. In practice, there are so many problems from so many areas that can be solved by proportions that 6 to 10 lessons of this size wouldn't be enough time to even show you the kinds of problems. But whenever you're faced with two items, in this case inches and centimeters, you ask yourself automatically after a while, are these so related that if I double the number of inches, I would have twice as many centimeters? And the answer to this is obviously yes. And if it isn't obvious, then this tells me what you're going to have to look up in an extra reading assignment. What is a relationship between these two? Then you suddenly realize this question, which came from a physical science class, is really a situation. They're saying, in this case, I have 8.7 inches, and I want to find its centimeters, so I'll call it C centimeters. So I ask myself, do I know any other situation where I know a relationship between inches and centimeters? Here are my two items, inches, centimeters. If I do, and if I know both of them, I can solve for the one I don't know. So looking at the back of any textbook, Peachy folder, dictionary, science book, you can find a table on conversion of units. And this is one that you would find, that 2.54 centimeters is 1 inch. Now note what they're really saying. They're saying for every 2.54 centimeters, there is 1 inch. Accurate, of course, to the nearest hundredth of a centimeter. So this, in fact, is my second situation I wanted. So let's see, I have inches first here, so I must have inches first down here, and here it is, 1 inch. I have centimeters here second, so I want the centimeter portion second, 2.54 centimeters. So here are my situations, inch, centimeters, inch, centimeters. What the order is not important as long as they're in the same order. Now, to form my proportion, it's just that simple. And with practice, using our shortcut we learned on the last lesson, we can simply find the diagonal without the letter. That's this one. So we multiply those two. 8.7 times 2.54, divide by the diagonal, the number on the diagonal with the letter, but that's just 1, and 1 divided into anything won't change it. So we can simply say equal, and we have that the number of centimeters I want is 22 point, if I wanted it to the nearest tenth, this is 0, the digit next to it is 5 or more, so I would round up. So I can say that 8.7 inches is 22.1 centimeters. So do you see you can use the fact of proportions and a conversion table now with this lesson to do any conversion you want to do, as long as you know it's a proportionate relationship. So that idea right there eliminates a whole host of problems that most students have at the beginning of almost every single science class. From business, proportion problems occur quite frequently. A candy shop wishes to mix 100 pounds. Now note, they're giving us a total here, and we mentioned that 2 lessons ago. A total of 100 pounds of nuts to consist of peanuts and cashews in a ratio of 5:2. How much of each is to be used? Well, let's concentrate on the peanuts, because if I find out how many pounds of peanuts I use, subtract that from 100, and obviously that gives me what's left, or the number of pounds of cashews. So our situation here is that I'm comparing peanuts, which I don't know, to total. Which I do know in this case. But I have 2 situations. I have what I want, ideally, and what I want in this specific case. So let's call the ideal situation our first situation. Okay, I want peanuts, and peanuts comes first, so I write it first, 5. But I don't want cashews here, I want the total here. Well, common sense tells me if I have 5 of peanuts and 2 of cashews, I have 7 of total. So here you have to be very cautious. I'm not comparing peanuts to cashews. I'm using the cashews merely as an intermediate step to get the total. So in my actual situation, I don't know how many peanuts I want, so let's call that P. But I do know the actual total is 100. So peanuts, total, in my 2 situations. Assuming they're all figured in pounds, there is my proportion. And after a while, you become just this good at it. You can look at the diagonal without the letter and say, aha, that's 500. And I'm going to divide this by 7. So my answer is, the number of peanuts is 500 divided by 7. Which is 71. If I went around to the nearest pound, that would be 71 pounds. And the cashews, of course, would be the rest of that 100 pounds, or 29 pounds. Now, understandably, I could have found the cashews first, then subtracted that from 100 to find the peanuts. The choice, of course, is yours. It doesn't take too much imagination to see what kind of problems might be like this, from everything from veterinarian science to garden mix to cooking to virtually every area of your home and your everyday life use this. Here's a problem that occurred to me in the grocery store just the other day, and it fits into the proportion pattern very nicely. See, we have 2 situations. We have a small box and a large box. The small box cost $1.90 and the large box cost $9.50. Which is the better buy? Well, you would normally assume that they'll probably both cost the same, or if anything, the larger box might be a little bit cheaper. Let's see if that's really the case. Situation 1, which is the small box. The 2 items we're dealing with is size, which is 1.5 ounce, to cost, which is $1.90. And situation 2 is the large box. Its size was 7.4 ounces, and its cost was $9.50. So now our question is, first, if they did cost the same, that means they're proportionate. That is, if I double the box or triple it, I should double or triple the price. And what we're asking is, did they do that, really? So we're really asking, is this true? Which means, is this cross product equal to that cross product? But we're more specific than that. We don't want to know just, is this true? We want to know which is the better buy. So what we do there is quite simple. We pretend like we don't know one of them. Let's call it P for the price and find out what this should be if indeed this was to be true, and compare that with the 950 and ask which is better. So we can do this with our shortcut, can't we? We find the diagonal without the letter. Here it is. So 7.4 times 1.9. Then we divide by the number on the diagonal with the letter. So we're going to divide by 1.5 equals, and we get 9.37. And that tells me that if the large box were priced at the same rate as the small box, it should have been priced at $9.37. And in fact, it's priced 13 cents higher. So in fact, the little box per ounce is indeed the better buy. Now, this whole process is involved quite frequently in store chains now, the larger ones, where at the bottom of the bin where the item is, you'll find a little tag that gives you the unit pricing. And what the store manager has done, usually through a calculator and or a computer, has simply gone through and worked, if you would, a lot of proportions to get everything to be the same unit price, or where they're not the same, to at least allow you to look at these two different unit pricings and to compare them with each other to ask which is the better buy. We did a survey once and found that in most freshman first-term science courses, probably 50% to 70% of all story problems in that science and 80 to 90% in business could be solved by proportions. So you see, this lesson is perhaps the most important lesson you've learned in this course. So become very good at it. It might be worth your while to become very fast at using the calculator with this as well. This is your host, Bob Fennell. We'll see you at the next lesson.